The first topic of this module is linear regression with the time series data, and we're dealing with the stationary variables. In this section, we are going to cover finite distributed lax models. We will have a discussion on serial correlation, and then we are going to discuss modeling strategies when dealing with the serially correlated errors. And we are going to introduce autoregressive distributed lax models as well. Then finally, we're going to discuss how to do forecasting and multiple analysis. First of all, let's have a look at the characteristics of the data that we're dealing with in this module, or time series data. The nature of the data are very important in statistical analysis because it largely determines the type of model that we can use. I believe most of you, if not all of you, have already studied linear regression. Linear regression, or OLS, is designed for cross-sectional data. That basically is a group of the observations that are collected at one point of time. So it's a cross-sectional. Time series data is just opposite. It's the observations of the same object, but across a period of time or at different point of time. So you have a different observational time, but it's from the same object. For example, if you look at your bank account balance over a period of time, so you may have bank account balance by the end of each month. So in each year, you have 12 observations. But those 12 observations are the observation of the same variable, which is your bank account balance. So that's a simple example of time series data. On that note, time series data have two important features that we really need to take into account when deciding which model to use. The first one is correlation, because those are the observations of the same object. So inevitably, the values are going to be correlated. There must be something, a large proportion of information are common among those observations. So we have this high correlation over the time, from time to time. Secondly, there is a natural ordering according to time. When you have a cross-sectional data set, you can order the data in any sequence. You can sort it, for example, you can sort it by any one of those variables in your data set. Your regression results are going to be the same, even if you use different ordering, because there isn't any natural ordering according to time in that data set for cross-sectional data. By definition, they are all collected at one point of time. However, for time series data, by definition, those are observations collected at different point of time. So the ordering of your data set is critical. You're not supposed to change the order of the data set without changing your model, or without telling your model that, oh, I changed the ordering. It is I'm not using this variable to order the data, but instead I use the other one. If you do that, more likely than not, the results are going to be different. So this is why later, when we need to do some practical questions, the very first step is to find an index or a variable that can indicate the time of each observation. So that's a crucial starting point for time series analysis because of this characteristic. There are also two important concepts that we need to introduce in time series analysis. The first one is the so-called dynamic relationship. The second one is the distributed effect. So let's go through the first one first. If you have a time series data and you run a time series model, you're trying to identify a dynamic relationship. By dynamic, we mean the effect is not a one-off. You do not have 100% of the effect right now at one point of time. Instead, the relationship actually can go beyond the current period and into the future. So we call it dynamic. Because of that, we have the second concept that's distributed, which means the effect is not in one period, but is spread out at several points of time. So you have to look at the effect at different point of time estimate them accurately, then put them together to form the full picture. Okay, so that's the same variable, but its effect comes from different point of time. And in a typical linear regression model, OLS model, you usually have one coefficient estimate corresponding to one variable. That's the overall effect, but it's not distributed. In time series analysis, you will have the same variable, but from its value will be from a different period, and they may have a different, those are lagged variables, put this way. So that's the term we're going to introduce later. And the lagged variables of the lagged term of the same variable will have a different coefficients. Those coefficients reflect the different effect from different period of time, and they're distributed. So you have to estimate them separately and put them together to form the full picture, and we are going to introduce some technique to do so. There are several ways to model the dynamic relationship, so how to capture those lagged effects. The first one is to include lagged independent variables in your regression model, just as shown on the slide. Okay, so this equation is called a distributed lag model because it has a lagged independent variables in it. So x1, x2, x3, or xt minus 1, xt minus 2. So this is the first type. You use this type of model when you suspect that the model is adequately, you have enough information captured in this model, which means those x's combined can reliably capture the effect or the relationship. However, sometimes you may have some missing variables, okay? And you may find this model useful. So you may notice that besides the lagged variable of x right over here, that those are the lagged variable of x, the independent variable. You also have the lagged variable of lagged term of y, which means there might be something in y that are not captured by x, but you still want to take that into account. This is the model that you want to use. We call this autoregressive distributed lag model, or ADRL model. So the autoregressive part refers to the lag term of y because it's a regression of y on itself, yt minus 1. And the distributed lag part refers to the lagged terms of x, as we mentioned before. There is a third way to capture this dynamic relationship, is to leave x and y's lag terms alone, but use the lag term of a residual. But bear in mind that the residual is a function of y and x. Okay, so residual basically is the difference between your observed value and estimated value, which means it's y and the linear combination of x. But that's in the previous periods. So t minus 1, t minus 2. So in this way, you captured anything that is kind of missing from previous estimation. Also, if you model correctly, the relationship doesn't have to be linear. Okay, so it's just the difference or the residual term of ET is more flexible than the last two one in certain circumstances. So in this case, ET is correlated with ET minus 1, and we will see if these errors are serially correlated or autocorrelated. So we're going to introduce models to estimate this, techniques to estimate this type of model as well. So to summarize, when we study OLS, or ordinary least square, or regression using cross-section data, there is an important assumption behind OLS. That is, the error terms must be uncorrelated. So for any two observations, their error term or y's must be uncorrelated. If we apply this to time series data, because those are observations at different point of time, so your subscript will be time instead of just individual objects. So the covariance or correlation between the error term from different point of time should be 0. But based on the discussion that I had on the previous three slides, it's clear that time series model or the dynamic models we introduced by construction have this correlation problem. So ET and ET minus 1, they are correlated. And it's clear violation of OLS assumption. This is why we need to introduce some new tools. There are some special circumstances where this condition can be met, so you can still use OLS to estimate time series data. That's basically the subject we are going to discuss in the first part of the lecture. However, in most cases, you probably won't be able to meet this assumption. That's the occasion when you need some new tools, which will be covered in the later part of this module.